Earlier we looked at what happens when an ionic compound dissolves in water, and the fact that the water molecules are so very polar that they're very attracted to these positively and negatively charged ions. Well, eventually then the ions separate from the solid crystal and they move around in the solution with their little shells of hydration. They're covered with water molecules, so they're really stable in solution. Well, anything that's got charged ions that are free to move will conduct electricity. So that could be like a metal, where metals have their sea of electrons, they're moving electrons. Or it could be a solution. In a solution, you've got these charged ions that are moving amongst the water molecules, and it conducts electricity. In order to conduct an electric current, you need moving charges. Now, the solid sodium chloride, for example, will not conduct electricity. It's got the charges, but they can't move. But when I dissolve the solid in water and the ions dissociate from the solid crystal, boom, moving charges conduct electric current. And so solutions that have these moving charged ions are called electrolytes. And yes, they do conduct electricity, which is why you're not supposed to drop your hairdryer in the bathtub, because even tap water contains charged ions. The strong electrolytes are solutions where the solid completely ionizes. The solute, whatever it might be, ionizes 100%. And so a good example is something like sodium chloride. When that sodium chloride solid sample completely dissolves, there will be no more sodium chloride molecules, no more sodium and chlorine bonded to each other. Everybody dissociates, 100% dissociation. I might even put that in there, 100% dissociation. We can write it as an equation. When I think about an ionic that's in solution, we often use that term AQ, aqueous, meaning dissolved in water. But when I see something like that, when I see sodium chloride aqueous, I have to picture in my head this. It's not really like sodium chloride molecules. It's never a sodium chloride molecule. It's this giant crystal lattice of oppositely charged ions. But when I put them in water, it dissociates. So I'm really thinking about this. Sodium ions and chlorine ions. Eventually, we're going to start looking at reactions that happen in solution. Single replacements and double replacements. They're really common. And so we have to really kind of understand what it means to be aqueous. Whenever I see that symbol, last year you probably just knew, oh, it's dissolved in water. But now we have to think about it in a little bit more accurate particle view. That it's really not any kind of bonded atoms that are swimming around in water. It's dissociated or separated sodium and chlorine ions that are swimming around in the water. And by saying that it's a strong electrolyte, we mean this happens 100% of the time. So if I had 100 sodium chloride molecules, I guess, or that there's 100 sodium ions and chlorine ions that are packed tightly in a crystal lattice, I put that thing in water, and by the time it fully dissolves, you would have 100 sodium ions, 100 chlorine ions, none of this. There's nothing that's chemically bonded together. It's all ions. Now, this reaction is a little different than what you may have learned last year as a decomposition, where you could have sodium chloride that decomposes to form sodium and diatomic chlorine gas. Totally different. This would have been solid sodium chloride with an intensely crazy amount of heat or electricity, would give you solid sodium metal and toxic yellow chlorine gas. Now, while that reaction might be really fun, and while maybe we could even balance it, you remember balancing these things last year? You were probably really good at it. That's why you decided to take another year of this. Now, we just have to make sure there's the same number of atoms of each element on both sides. So there's 1 chlorine, and then there's 2 chlorine. So if I want 2 chlorine on both sides, the only thing I can do is add those coefficients. I can't change the formula of sodium chloride. But then by fixing my chlorine, I also doubled my sodium. That's why they call it balancing. You work it side to side until we have the same number of sodium and chlorine atoms on each side. That is a decomposition. Decomposition. And they're great, but that is a chemical reaction because I am forming something that is totally different than the original substance, and the only way I could reverse it is with another chemical change. That's not what happens when you put an ionic compound in water. Instead, we get the dissociation. Here it is. This top reaction, that's the dissociation. That's a physical change. I mean, all I did was separate the ions, but they have the exact same structure. All I have to do now is evaporate the water molecules, and the ions can suck back into the original solid. No change of structure for the sodium or the chlorine ions. I just separated them now. So we don't want to do the decomposition. I mean, it's a great reaction, but it's not what happens when something dissolves in water. Instead, we form lots of charged ions. And so all of these ionic compounds that are highly soluble and form lots of charged ions will also conduct lots of electricity. Now, the other thing we should mention is that, like, when we say that we're writing the equation for a dissociation in water, we don't put the water molecules in the equation because the water molecules aren't changing in any way, and the water molecules are surrounding each ion, but they're still H2O molecules. And in an equation like this, we're really just trying to show what changes. So if you see something that talks about a dissociation of sodium chloride in water, well, you don't have to put the water molecules in. They're not changing in any way. Instead, we just want to show the original ionic solid mixing with water molecules to have a total formation of ions. That's what it means to be a strong electrolyte. Everybody splits to form lots of charged ions.